All right, so well log correlation is an important step in many geologic and geophysical interpretation methods, such as building geologic models and time depth conversion. And in the past, well log correlation was commonly done by hand, but due to the rapidly increasing number of logs, we now require automatic methods. Existing automatic methods can be divided into two main groups, those for correlating a single pair of logs and those for correlating many logs. And our method uses pairwise correlations in order to simultaneously correlate many logs. But before I describe our method, I'd like to explain what I mean by correlation and define a few terms I'll be using throughout my presentation. And to do that, I will use logs from 13 wells in Teapot Dome with locations shown here. And first, I'd like to look at just 6 density logs along the cross-section shown here. So well log correlation is the process of determining corresponding depths among logs. And a single set of such corresponding depths implies that the sediments at those depths were deposited at the same time. Here I've drawn just 3 sets of corresponding depths, excuse me, which I have interpreted to be the tops of 3 formations in Teapot Dome. And using this correlation, we can get an overall idea of the subsurface structure. Now let's look at all 13 density logs. But instead of plotting them by distance between the logs, let's plot them by log index, as shown here. And recall that sediments at corresponding depths were deposited at the same time. And so we can map these logs from depth to time to get an image such as this, where the values of relative geologic time here are arbitrary. All that we are saying is that sediments with greater relative geologic time were deposited before those with lesser relative geologic time. And now for any constant relative geologic time in this image, we have a set of 13 corresponding depths, 1 for each log. Now, within one oil field, well logs often appear to be just statically shifted versions of one another. So to align logs, one might think to shift each log up and down by some constant amount. And what you'll get is an image like this, which gives a decent alignment. However, there are some very important misalignments here. And I'll zoom in so you can see this in more detail. Now notice at a relative geologic time of about 0.8, the depths in log 2 are shallower than their corresponding depths in log 3. And down around relative geologic time of 1.4, the opposite is true. Depths in log 2 are now deeper than their corresponding depths in log 3. And so what this tells us is that we need time varying shifts in order to correctly align all logs. And in fact, that's how we made the image shown here, by applying time varying shifts. And again, recall that along any relative geologic time in this image, we have a set of corresponding depths. And here I've drawn the same 3 sets of corresponding depths, which I showed earlier, referring to the 3 tops of the formations. And once we have corresponding depths, we can map them from time back to depth to get our final correlation. Now, recall that I mentioned that we use pairwise correlation in order to simultaneously correlate many logs. So I'd first like to explain how we perform this pairwise correlation. And to do that, I'll use the 300-meter subsections of logs 1 and 2 within the blue rectangle. And there are many existing methods for which we can use to perform pairwise correlation for a single pair of logs. And we choose to use dynamic warping because it is robust in the presence of geologic gaps due to things such as erosion or faulting. But before I describe how we use dynamic warping, I'd like to change notation a little bit, and I'll now refer to the values within the logs as f of little I, and f of little j, where capital I and j are the indices of the logs, and little I and j are the indices of the depths within the logs. Now you may know that the first step in dynamic warping is to compute alignment errors between each sample in log I and each sample in log J using the equation shown here, and you produce an image such as this. And dynamic warping uses dynamic programming in order to find an optimal path, which is a sequence of ij pairs that minimizes the sum of alignment errors along that path. And in our case, this gives us a sequence of corresponding depths. Now, if we look at just one point on this path, denoted by the orange dot, this point tells us that a depth of about 1,000 meters in log 1 corresponds to a depth of about 1,040 meters in log 2. And using dynamic warping, we can find a sequence of all such pairs of corresponding depths. Now, it's common in well log correlation to use the L2 norm in the alignment error calculation, thereby squaring the difference between log values. So when large measurement errors are present, alignment errors become huge, and this can be seen by the bright white vertical and horizontal lines in this image. And these large alignment errors act as barriers and could change the optimal path, and thereby you could end up with misaligned logs. Now, because we do not pre-process the logs to remove any large measurement errors, we choose to use a norm less than the L2 norm in order to reduce the effect of large measurement errors on the alignment. And for the 13 density logs I showed earlier, we found through experimentation that the L1/8 norm works best. Now, although there are many possible warping paths, I'll use a simple schematic with just two paths shown here, path A and path B. What you'll notice is that path B is much shorter than path A. So when we sum alignment errors along the paths, we may find that the sum at the end of path B is less than the sum over path A. And so path B could be optimal simply because it's shorter. And to avoid this, many methods require that all paths pass through the upper left and the lower right-hand corner of the IJ coordinate system. But this requires some other methods, such as manual picking, in order to determine corresponding depths at the tops and the bottoms of the logs. Instead, we use a rotated KL coordinate system, where K is equal to J plus I, and L is equal to J minus I, where L is the measurement of lag, or a difference between two depths. And now we have a new coordinate system on which to compute alignment errors. And we can again sum alignment errors along all paths and choose the path with the minimum sum at the end of the path. And here you'll notice that now all paths have the same number of steps in the K direction. And so we eliminate the bias of a shorter path being optimal simply due to its short length. Now let's look at the alignment errors for the same 300-meter subsections of logs I showed earlier, but now on the KL coordinate system. And we can zoom in to see this in more detail. And we can again find the optimal path, which here lies at about 40 lag. And this tells us that the depths in log 1 are about 40 meters shallower than their corresponding depths in log 2. And using dynamic warping, we can find a sequence of all such pairs of corresponding depths. And here I've drawn just 3 pairs of corresponding depths. Now, I've shown how to find sequences of corresponding depths for any log pair, but what we are more interested in is how to simultaneously correlate many logs. Here again are the 13 well locations I showed earlier, and just for reference, the 2 logs we were working with are circled in red. And a common way to correlate a set of logs is to first perform pairwise correlation between logs 1 and 2, then 2 and 3, 3 and 4, and so on, using the earlier correlations as constraints for the later correlations. But the problem with this is that any errors made early on will propagate through to the later correlations. And so the final correlation depends upon the order in which these logs were correlated. And for these 13 logs, there are over 6 billion different ways in which we can order the logs. And so it's possible to get over 6 billion different answers. But what we want is one consistent correlation that doesn't depend upon the order of the logs. So instead, we can perform pairwise correlations between all possible log pairs and then maintain consistency among these pairwise correlations. Here, for the 13 logs, we have 78 possible log pairs denoted by line segments here. And to explain what I mean by maintain consistency, I'll use logs from the 3 wells circled in red. Now, if we perform pairwise correlation between logs 1 and 2, we may find that a depth zi in log 1 corresponds to a depth zj in log 2. Similarly, when we correlate logs 2 and 3, we may find that zj also corresponds to a depth zk in log 3. So, when we correlate logs 1 and 3, we expect zi and zk to correspond. But this doesn't always happen in automatic methods. And the use of dynamic warping to correlate these 3 logs is similar to the method for registering 3 multi-component seismic images described by Stephen Compton and Dave Hale. And we could use a similar method here, but it would require applying constraints, where the distinct path among these 3 corresponding depths I've drawn here would be used as one constraint. But what if we have 4 or 5 or 13 logs? There are in fact over 5 billion different ways in which we can draw a distinct path among 3 or more wells in this set of 13 wells. And so this gives us over 5 billion constraints per set of corresponding depth. And if we have just 1,000 sets of corresponding depths, this gives us over 5 trillion constraints, which are then used in the alignment error calculation. Additionally, the alignment error array increases in dimension with each log, and so dynamic warping becomes just too costly to use for well log correlation. And we require some other method to maintain consistency among these pairwise correlations. So let's look back at logs 1 and 2, and if we perform pairwise correlation between these logs as described earlier, we may find that depth zi and zj correspond. And so to align these depths, we can shift zi down by some amount s of zi and zj up by some amount s of zj. And essentially we get the equations shown here, where we refer to the depth after aligning as relative geologic time. Now, because we use dynamic warping to find an optimal sequence of corresponding depths, we can say that these relative geologic times are equal, and therefore these equations are equal. And moving the unknown shifts to the left and the known depths to the right, we get the equation shown here. But this is just one equation for one pair of corresponding depths in one log pair. And in fact, we have an equation like this for every pair of corresponding depths in every log pair. And in general, the number of equations is much greater than the number of unknown shifts. For the 13 density logs shown earlier, there are about 150,000 equations and just 25,000 unknown shifts. And so this leads us to the following least squares problem, where each row in the matrix DS has only 2 non-zero entries, a 1 and a -1, referring to the signs of the shifts in the above equation. And because we have many more equations than unknown, we don't expect all equations to be satisfied, and therefore this relationship is just approximate. And we can find the least squares solution to this problem by solving for s in the normal equations shown here. And doing so will result in depth shifts for which, when applied, will align all logs simultaneously. However, aligned logs such as these will remain aligned if they are shifted or stretched or squeezed. And so our solution is non-unique, and we must remove this unnecessary shifting, stretching, and squeezing. Now, I showed one way to align logs, and that is to find relative geologic times tau for every depth z. But we can go the other way and find corresponding depth z for every relative geologic time tau, using the equation shown here. And depth shifts s and relative geologic time shifts r will be equal if the logs are related by only constant shifts, but as I showed earlier, that doesn't typically happen. So S and R can be related as shown. Here again is the depth pair equation from earlier, and now using the relationship of S and R, we can construct a new depth pair equation. And now we have a choice. We can solve for depth shifts S, or we can solve for relative geologic time shifts R. And I don't have enough time to go into the details, but as it turns out, we must solve for relative geologic time shifts R in order to align all logs and remove the unnecessary shifting, stretching, and squeezing that I showed earlier. And the details as for why can be found in my thesis. So now we have the same number of equations, the same number of unknown shifts, and so we can solve a similar least squares problem shown here to find relative geologic time shifts R that align all logs simultaneously. Here again are the 13 density logs from earlier, and after applying these shifts R, we get the alignment shown. And the most apparent alignment here is probably that at about 1.4 with the blue density layer that corresponds to the Crow Mountain Formation. But let's zoom in to where the alignments are not so apparent. Here you can see that we're aligning relatively thin, consistent density layers. And I'd also like to point out that we have done no pre-processing to the logs, and so large measurement errors still exist, and I pointed out just 3 here. And it appears that these large measurement errors have had no negative effect on the overall alignment of the logs. Now, our method can be used for any number of logs and any type of logs. Here we have 3 sets of logs, 13 density logs, 11 porosity logs, and 5 velocity logs among the 13 well locations I showed earlier. Now, you could use our method to align each set of logs individually, but what you'd end up with is 3 different relative geologic time scales for which you would then have to correlate to one another. But instead, you can use our method to simultaneously correlate logs of all types. And to do this, we again begin by performing pairwise correlations between all possible log pairs within each individual log type. And this results in 142 different log pairs. And from these pairwise correlations, we again get sequences of corresponding depths. And while there are some minor modifications we must make to align logs of different types, the important thing to know is that from these sequences of corresponding depths, we can construct depth pair equations similar to those I showed earlier, but the main difference is that now we have even more equations while the number of unknown shifts is unchanged, and so we can solve a similar least squares problem to that I showed earlier. Now here again are the 3 sets of logs, density, porosity, and velocity. And by applying relative geologic time shifts to these, we can align them as shown here. And now notice that all 3 sets of logs share the same relative geologic time scale. And so we can correlate across log type for any constant relative geologic time. So to summarize, I'd like to point out key differences between our method and existing automatic methods. We first begin with pairwise correlation in order to find sequences of corresponding depths for all log pairs. And in the alignment error calculation, we use a norm other than the L2 norm in order to reduce the effect of large measurement errors on our data. We also compute alignment errors on a rotated coordinate system to eliminate any need for manual interpretation. And once we have these sequences of corresponding depths, we can use them in a least squares problem to solve for relative geologic time shifts that ultimately align all logs simultaneously. And once we have aligned logs, we can now find set of corresponding depths for every constant relative geologic time in this image, for which we can map from time back to depth to get our final correlation. Thank you.